recording. I'm not sure if you guys reviewed these chapters. I think a bunch of you guys reviewed the chapters prior to last week's lecture. Not necessary, but if you did review these, this is pretty much just going to be a recap of everything that is in your textbook for chapter 4 and 5. This stuff starting out with physics is really kind of boring because we're not really talking about image acquisition quite yet. Once we get into the things that you can really piece together, like while we're scanning, that's when physics is going to start to kind of click a little bit more. So if you're reading through these first 4, 5, 6 chapters and this stuff just seems very straightforward and kind of repetitive and redundant and a little bit boring, that's because it is, and it will start to make a little bit more sense when we're getting into how these theories and these techniques really do create an image in a few chapters. So last week we talked all about how sound waves behave, how we describe sound waves, but we were really just talking about sound waves in general. We weren't really talking about how we use them in ultrasound. We were talking more about what we call continuous sound waves, and today we're going to be talking about something a little bit different. We're talking about pulsed sound waves. So what actually is pulsed sound? This is what we are using in ultrasound. This is what our sound source or our machine is creating. And we're basically doing this talking and listening type of relationship between the sound source and the original sound wave and then the rest of the body. So we're giving the system time to listen and receive those reflected sound waves back to the system. So pulse sound, this is when our system creates these really short pulses of sound waves to create our images. Now, this isn't just sending out one sound wave. This is sending out a unique collection of sound cycles that are going to travel together for that duration of that pulse. So a pulse can be 1 cycle, it can be 5 cycles, it can be 15 cycles. When we're talking about pulsed sound, it's just like one punch of a bunch of sound waves coming out of that sound source. Now, when we are talking about sending out this collection of cycles, we want to be aware of when this is starting and when this is ending. So when is our pulse beginning and ending? Everything that happens during that duration is what we're going to be talking about today. And then we're also going to be talking about what happens when we're not sending in a pulse. So we have these individual cycles that are going to travel together to create that entire pulse. As we said, that could be 1 cycle, that could be multiple cycles, usually going to be multiple when we're talking about ultrasound. And then we're also taking into consideration the talking and the listening. So the talking is when our system is sending in that pulse, and listening is a brief period of time after that pulse has ended where we're not sending in a signal and we're waiting for reflections to come back to the transducer. So this is also known as our on and off time, or our transmitting and receiving time. So let's look at our next slide here. So that top wave, that's a continuous sound wave. That's pretty much what we were talking about last week, right? We talked about wavelength, we talked about frequency, we talked about the amount of time that it takes to complete 1 cycle. We talked about how many cycles can occur in 1 second, right? We were talking about it as if the sound wave was continuously traveling. Today we are talking about that short collection of cycles that the system is sending out in a pulse. So if we look at our example on the bottom, that is an example of our pulsed wave. We are sending in the same number of cycles, but look at how much more compressed and condensed that is. We're also taking into consideration how long our system is listening, right? So we have our pulse that we sent in, our collection of cycles, and then we have a period of time where we're not sending in any sound waves. So let's talk about some parameters, or how we describe pulsed sound waves. We talked about our 7 parameters last week, and that was, again, just talking about how we categorize and describe the behavior of regular sound waves. Now we're talking about how can we categorize a pulsed sound wave, right? How do we characterize that collection of cycles that are being sent in from our system? We do so by our 5 parameters. So we have pulse duration, we have PRP, which is pulse repetition period, we have PRF, which is pulse repetition frequency, we have duty factor, and then we have spatial pulse length. So we have 7 parameters for acoustic sound waves, right? Just talking about sound waves in general. And then we have 5 additional parameters to describe pulsed sound for ultrasound. Let's talk about our first one, pulse duration. This is exactly what it sounds like. How long, how much time does it take from one pulse to start to the end of that pulse? How long is that pulse, right? So we're talking about units of time here. And as we know with ultrasound, everything is moving so quickly. So we're talking about microseconds with this. The average value range is going to be about 2 to 4 cycles per pulse. So really every pulse that our system is sending in, we're sending in at least 2 and usually a maximum of 4 cycles per pulse. Now, depending on what type of transducer we're using or how far into the body we're looking, we are going to tell the system to send in more or less pulses. So don't get confused with that. We will get to that in a second. Pulse duration is just the time from the start of that collection of cycles to the end of that collection of cycles. This is going to be non-adjustable, so it's only going to be controlled by that ultrasound machine and partially on the transducer. When we learn about transducers, we're going to learn about all of the components and the crystals that make up the transducer. And depending on the composition of our transducer and the components in it, that's going to have a slight effect on this pulse duration. Again, we'll get to that when we get into our actual transducer lectures. Now, pulse duration is going to be directly proportional to the number of cycles in the pulse. So if you have more cycles in the pulse, well, of course, that's going to increase the amount of time that it takes from the start of that pulse to the end of the pulse, right? It's going to be directly proportional. That means it's also going to be directly proportional to period. So the amount of how long it takes to complete that cycle, right? So if we have a higher period or a longer period, that means our pulse duration is going to be longer because of the amount of time that it takes for one cycle to complete. Right? So if we have 4 cycles in there and each cycle has a higher period, well then of course we're going to have a higher pulse duration, a longer pulse duration. It's going to be inversely proportional to frequency. So if we have a really low frequency, we know that those waves move a little bit slower, right? So we're completing less cycles in that 1 second time frame. So therefore our pulse duration is going to be higher. It's going to be longer, take longer to complete that collection of cycles because our frequency is very low and that wave is moving very slowly. You can calculate your pulse duration. So you're taking your number of cycles and you're multiplying it by the period. You're usually going to be given that information in terms of a registry question. And then you can also, if you're not given period and you're given frequency instead, you know that you can calculate that using the number of cycles divided by the given frequency. So just know that interchangeable equation to calculate this. So what would we prefer when we are imaging? Do we want a long pulse duration or do we want a short pulse duration? It all depends on what you are looking for. Ultimately, a shorter pulse duration is going to give us better image accuracy because it's sending in those same number of cycles in a shorter period of time. So this is going to be cycles that have short periods, short given periods, or we have fewer cycles that are trying to get through in that collection. Now, when we have a long pulse duration, this means we have many cycles or we have cycles with long periods. So as we know, this is going to be inversely related to that frequency, right? And frequency, we want the highest frequency possible for our appropriate depth because we know the higher the frequency, the better the image detail. So it's that give and take balance of what are we looking at, where are we trying to get that sound wave to go, and how is that sound wave going to behave as it's traveling. So if we look at the picture on the bottom right, That red arrow, is that representing that top image? Is that representing a short pulse duration or a long pulse duration?
Long.
Good, right? Pretty obvious in comparison. And why do we think that that's longer? What are two things that are leading us to believe that that is a longer pulse duration than the pulse on the bottom?
Has more cycles.
Yep, it has more cycles. And what about those cycles? Let's compare those to the bottom.
Is it that they're like longer and more spread out?
They are. So what would that be? If the cycle takes longer, takes more time to complete,
The
that has
period
a
is longer?
good, that has a longer period, right? So it all depends on what we're looking for. Again, we want that shorter pulse duration, but as we know with that, as our pulse duration decreases, our frequency is going to increase, right? We're going to have better image accuracy, better image detail, but what are we going to lose from that?
Image accuracy?
Nope, we're going to have really good image accuracy with short pulse duration because we have a higher frequency. What is going to compensate for that? What are we going to lose when we have that higher frequency?
Would it be like less imaging depth into the body?
Good. So less imaging depth, or when we're talking about physics, less penetration, right? So good. Let's move on to our spatial pulse length. So this is talking about the distance that it takes for the pulse to start and end. So the pulse duration is the amount of time that it takes to complete that collection of cycles, but the spatial pulse length is what is the distance that it takes. So if you are given an example, you're given a diagram of a wave that's showing pulsed sound waves, and you are trying to figure out, okay, well, what are they asking me to look at? Look at the units that they are giving you. Are they giving you microseconds? If so, are you going to be able to calculate spatial pulse length? Probably not, right? Because it's in units of time. So these are the things that are going to make the slightest difference in your answer when you are taking my quizzes or when you are taking the SPI registry. So look for those little things that are going to help you determine what the question is looking for you to calculate. So if you're looking at a wavelength and it gives you distance or gives you units of distance or length on your x-axis, you know you are looking for some type of measurement of length or distance. So the average value range for a typical pulse is going to be 0.1 to 1 millimeter. That's very, very small, right? So everything we're talking about is very short and very fast. So we're really kind of talking about minute differences in a long wavelength or a short wavelength in terms of spatial pulse length. This is not going to be adjustable, and it's controlled by our sound source and also our medium. So what type of tissue are we looking for? Our penetration is going to have a factor on this. As we know, our sound wave weakens as it travels, so that is going to have an effect on the spatial pulse length. Now, the SPL is going to be directly proportional to the number of cycles in the pulse. So, of course, the more cycles we have in that collection for that pulse, the longer it's going to be. It's also going to be directly proportional to wavelength. So, if we have a long wavelength, a greater wavelength, of course, that's going to make our spatial pulse length longer, and it's going to be inversely proportional to frequency. So, the longer the distance of this collection of cycles, the longer this length or the longer this wavelength of each cycle, the lower our frequency is going to be, okay? You can again calculate your SPL if you are given your number of cycles or your wavelength. That would just be multiplied together. And let's take a look at this a little bit further. So a longer spatial pulse length, as we just said, is a pulse that has many cycles, or it has cycles with longer wavelengths. Shorter spatial pulse lengths, of course, fewer cycles or cycles with a shorter wavelength. And again, similar to that pulse duration, when we have a pulse that has a shorter pulse length, we are going to have better image accuracy. This is all depending on what we are trying to look at. If we're trying to send that sound wave further into the body and we're trying to get that penetration, we want a longer wavelength. We want a longer spatial pulse length to give that sound wave the power and the energy to get further into the body. Now, we want to make sure that we are also getting appropriate image detail. So we're walking that fine line. This is why we're constantly choosing which transducer is going to be better for what exam we are imaging. We don't want to use a curved transducer for a thyroid because our curved transducer, our range on that in terms of our frequency and our wavelength is going to be lower. Whereas a linear transducer or the higher frequency transducer is going to be better for that superficial structure because we're going to have that shorter pulse duration and that shorter spatial pulse length. So those are the things that, although we cannot adjust these types of parameters, these are the things that we can control when we are selecting the appropriate transducer for our exam. So pretty self-explanatory image here. If you are given units of distance on your axis, you are going to be able to calculate that by multiplying it with these cycles. Moving into our pulse repetition period. So this, although it has the same term, is actually unrelated to the period of a sound cycle itself. So what actually is this? It's the time from the start of one pulse to the start of the next pulse. So this means that we are looking at the amount of time that it takes for this pulse to talk and then also listening, right? So we sent the pulse in, we're taking into consideration the amount of time that that took to send the pulse in, but now we are also looking at the time that it took to listen before our next pulse gets sent in. This is going to be measured in units of time, and the typical value range is obviously going to be longer than our pulse duration because our pulse duration is the amount of time that it takes to send in just the pulse. With pulse repetition period, we're looking at the amount of time it takes to send the pulse in, but also the amount of time that our system is then listening before the start of our next pulse. So it's going to range from about 100 microseconds to 1 millisecond. So it's going to be a little bit longer amount of time. It's actually 100 to 1,000 times longer than just the pulse duration. So that just goes to show you how long our system is actually listening and waiting to receive those reflections back from the body. So this is going to be controlled by the sound source and the imaging depth. So this is going to be adjustable on our end. The shallower our depth is, so the less depth we have on our image, the shorter our PRP is going to be. The deeper into the body we are looking, the longer our PRP is going to be. So this means that our imaging depth is directly related to our pulse repetition period. Now, if you think about that, if you are imagining yourself at the school and you are standing at Maria's office and I am standing down at Ellen's office, right? It's going to take us, and we're trying to talk to each other down the hall, it's going to take us longer to listen to each other because we're further away. But when you are standing at Chelsea's office and I am standing at my office, we are so much closer together that we don't have to listen for as long, right? So if you think about it, if you're really far away from your friend down a hallway and you're trying to talk, you're going, what? It takes your brain a second to process what they're saying because they're so far away. It's going to take that much more time for that sound to get to you. You're going to be listening for that much longer than if you are right next to that person. You have that shallower depth. You have less distance between you, that you don't need to be listening as long. Okay, does that kind of make sense a little bit with that? So here we have our textbook examples. These are all images right from your textbook if you haven't reviewed these chapters yet. So these are going to seem very familiar to you if you have. But this picture on the left side, again, picture yourself in this office, right? We have that really long hallway. So you are at Maria's office here. I am at Ellen's office here, right? We're further away from each other. We have deeper imaging. We're covering more space, right? So it's going to take our pulse that much longer to send itself in. I'm sorry, it's going to take our pulse repetition period that much longer to listen. Our pulse duration is staying the same as this one, right? It's taking the same amount of time to get the pulse in, but we're just listening for longer in between the two. Whereas our shallow imaging, we can go back and forth, talk, listen, talk, listen, talk, listen. When you're further away, you're talking, and then you're waiting and listening for that sound to get back to you. Now, if we look at our picture on the right side, this is showing everything that we've learned up until this point all together with one, right? So the blue arrow is showing our pulse duration, okay? The amount of time, if we're given time on this axis, the blue arrow is our pulse duration. Our black arrow is our receiving time or our listening time, and the red arrow is both of them together, pulse repetition period. So the red arrow is going from the start of this pulse to the start of the next pulse. Okay, moving into pulse repetition frequency. So like pulse repetition period, this is actually unrelated to the term that's in its name. So it's unrelated to the frequency that we have learned about so far. So this is the number of pulses, not the number of cycles in the pulse, that the system is transmitting into the body each second. Okay, so the pulse is the collection of cycles. How many collection of cycles are we sending into the body in a 1 second time frame? So it's similar in concept to regular frequency, right? Where we're talking about how many sound waves can we send in 1 second. But this is talking about how many collections of sound cycles can we send in 1 second. So this is going to be reported in units of frequency. So this is going to be reported in units of hertz. The value range is going to be, that should say Hz, but it is 1,000 to 10,000 hertz. It's going to be controlled by our sound source and our imaging depth. And yes, we can adjust it because we can adjust our depth while we're scanning. So we are going to see with deeper imaging, we have a lower PRF. With shallow imaging, we have a higher PRF. So this means that when we decrease our depth, right, for shallow imaging, we are increasing the number of pulses that we're sending in that 1 second. So we are increasing our PRF. So these two are inversely related to each other. Now, if we look at our deeper imaging, we see that, again, we have to take into consideration all of that listening time. So we're not going to be able to send in as many pulses within that 1 second time frame. So we're going to have a lower PRF. We have a lower pulse repetition frequency. So give me a second. I'm just going to flip over to my regular PowerPoints so I don't give myself a migraine trying to look at this slide. Okay, so we have talked about PRP and we talked about PRF, right? How are the two working together? What do we prefer? How do we calculate the two? Does one have a factor on the other? Well, they're going to be inversely related to each other. So when we have a longer PRP, this means it takes a longer amount of time, we are going to have a lower PRF. This means that a longer period of time, we can't send in as many cycles or as many, pulses in that 1 second time frame. So we're going to have a lower PRF because the PRP is too long. Now, when we have an increased PRP, that means we are also going to have a decreased PRF, as I just said. When you have a shorter PRP, right, the amount of time that it takes is less, you can send in more pulses into the body. So you're going to have a higher PRF. The two of them on a mathematic level have a reciprocal relationship. So this means that if you multiply them together, they're going to equal 1. That's kind of like the standard basis for a reciprocal relationship. You can calculate the other if you know one of these parameters. So if you are trying to calculate your PRF, but you are given your PRP, you are just going to do 1 divided by your PRP, and that will give you your PRF. Same thing when you are looking to calculate your PRP, but you are given your PRF. You can use that equation right there. They're usually going to give you the information in order to get to this point. You also may have to take it a step back to calculate your PRP or your PRF. So they may give you a wave that you have to look at, use those units to help you in order to calculate one of those, so you can plug that into this reciprocal equation. Next, we have duty factor. So this is a really bizarre parameter, and this is really not like any of the other ones that we have learned about so far. This is the percentage or the fraction of time that the system is transmitting a pulse. So different from PRP, right? The PRP is talking about the pulse duration amount of time and the amount of time that the system is listening. This is looking at getting a percentage over your total time that the system is transmitting that pulse. So it's not the pulse duration itself, it's getting a percentage. So the typical value range is going to be 0.2 to 0.5%. This means that the system is always going to be listening slightly more than it's talking. And we kind of saw that with some of the examples and some of the images on the previous slides. We are always listening. We're waiting for those reflections. We're waiting to see how that sound wave interacted with the body. And we're not really sending in this constant continual sound wave. We want to be listening. We want to be taking those reflections in and processing them to get an image. Duty factor is going to be controlled by the sound source and the imaging depth. So of course, anytime we can adjust our depth, it is going to be adjustable on our end. Duty factor is going to be inversely related to imaging depth, similar to the other relationships that we have learned about so far, PRP and PRF, having those particular types of relationships with imaging depth. So as we have a greater depth, we are going to have a shorter duty factor, right? Because the deeper into the body we're looking, the more we are listening. So that percentage of time that the system is sending in a pulse is going to be less than when we have shallow imaging. When we have shallow imaging, we have a higher PRF, shorter PRP. Therefore, we are going to have a greater duty factor, a higher duty factor. So it is a unitless type of parameter. We can give it a percentage, but we are usually only giving it just kind of its own non-unit, I guess, if that makes any sense. So basically, if you see a number and you're not given a unit with it, it's safe to assume that they are talking about duty factor. When we are in our world, we are always using pulsed wave ultrasound. There is a world in echocardiography and in therapeutic ultrasound where we are sometimes using that continuous wave ultrasound. So if we go all the way back to the beginning of the PowerPoint here, and we look at this top picture, that's a continuous wave ultrasound, right? There's no listening time with that. It's just constantly sending in that sound wave. And there are a few reasons why we would need continuous wave ultrasound, but not in our day-to-day job, not when we are doing clinical imaging. But if we were to, let me go back to our slide here. If we were to use continuous wave ultrasound, you are constantly sending in sound waves, right? So your percentage is going to be 100 for continuous wave ultrasound, or 1. That is only for continuous wave ultrasound because it is not listening at all, right? It's just only talking. It's only transmitting the sound wave. Now, again, with continuous wave ultrasound, if you're not using the transducer, right? You're not sending in that continuous wave into the body, your value is going to be 0 or 0%. So it's a little bit different when you're using pulsed wave ultrasound, because now we are saying, okay, I'm talking, but yet I'm also listening. And how much of this time am I actually talking for? Kind of like when you get your schedule for each semester. You take a 4-credit course and you assume that you're going to be in class for 4 hours, right? But the teacher only talks for an hour. That is the duty factor, that however much percentage that would equate. Okay, kind of bizarre. But this is a very interesting, and this parameter usually confuses people a little bit. So you can calculate your duty factor. If you're trying to get a percentage, you would take your pulse duration divided by your PRP, and you would multiply that by 100. The pulse duration is also going to be equal to the time to transmit one pulse, right? So that's what we're looking for. And the PRP is going to be the time to transmit one cycle. So that's going to be able to calculate how much of that time are you actually talking for? How much time is that system taking to send in that one pulse, that one collection of cycles? And here again, our picture from our textbook. So do we want shallower imaging? Do we want deeper imaging? There's so many things that we've learned about so far in this PowerPoint. We're kind of assuming that deeper imaging is bad, right? Because it's not giving us the greater image accuracy. But as we know, we have to get that sound wave into the body to give a full evaluation for that patient. So it's this fine line of keeping our depth as shallow as possible, but also making sure that we are obtaining the image that we need to obtain. So when we have shallower imaging, let's kind of piece all of these parameters together. You have shallower imaging, you have more talking from the sound source, you have less listening. Remember, my office, Chelsea's office, right? We can talk back and forth a lot faster, right? So we're not listening for as long. We're going to have a shorter PRP, right? The amount of time between the start of one pulse to the start of the next pulse. We're going to have a higher PRF because of that shorter PRP, right? Less of a distance that everything has to travel, so we can send in more sound waves or more pulses per second. So we're going to have that higher PRF, and then we're going to have a higher duty factor because again, we don't have to listen as long, right? Our sound source can talk for more because it doesn't have to listen as much than with deeper imaging. Now, deeper imaging, that's all going to be opposite. So you're listening more, you're waiting for those reflections to come back into the transducer. You sent those reflections, you sent that sound wave so deep into the body that of course it's going to take longer for those reflections to come back to you, right? And then you can talk again. So we have more listening, less talking. We have a longer PRP. The amount of time that it takes when we're including that greater listening time is going to be higher. So therefore, we're going to have a lower PRF. We can't send in as many pulses as we want to because we're listening and we're waiting for those reflections to come back. And therefore, we're going to have a lower duty factor. The amount of time that the system is going to be transmitting a pulse is going to be less than if it were with shallow imaging. So piecing some of these components together with our picture here, our blue arrow on top of that pulse is going to be our duty factor. And then our red is still showing us our PRP. Now, if the axis was giving us time, what would our blue arrow indicate? Would it still indicate our duty factor?
Wouldn't it be the spatial pulse length?
No, if the axis was giving us time. So the amount of time that it would take to complete that cycle, that blue cycle, what would that be?
Would it be the period?
Nope, because remember the period is going to be when we're looking at just one sound cycle. With this, we're looking at a pulse. So we have a collection of sound cycles. So what would that be if we had time, if it was giving us time on our axis there?
Would it be the pulse repetition period?
Not quite. Pulse repetition period is going to include that listening time, right? So that would be our red arrow.
Would it just be the pulse duration?
Yes, good. So that's going to be our pulse duration if we were given time. Now, if we were given units of distance, the blue would be our spatial pulse length. Okay, so the length that collection of cycles takes as it's transmitting. So I don't expect you guys to get this stuff right away. You kind of have to like walk through this. It's kind of like an onion, right? You got to peel back those layers and be, understanding of what each wavelength is trying to tell you and the information that you're given on each wavelength. So tricky stuff and bizarre stuff. This isn't really stuff that we've talked about while we're scanning. So next we're going to move into intensities, and intensities is usually a least favorite topic. And that's because it's not really going to make sense to you guys right now until we get to sound beam characteristics. Once we get a few chapters in and you come back to this chapter, this will make a little bit more sense to you. So we kind of talked a little bit about intensity last week. We know it's going to be a bigness parameter, right? It's talking about that strength of a sound wave and the overall impact that it's having as it's traveling. So there are different ways that we are measuring intensity, we're reporting intensity. What is the importance of intensity? Why do we care, right? We're not X-ray, we're not radiating people, we're not CT. We don't need to worry about the power of radiation, but we do need to be considerate of the overall intensity and the strength of our sound beam in clinical exams. We can't let the intensity of our beam reach beyond certain parameters, because that's when we fall into some of our bio effects. And we'll get to bio effects at the end of the semester. But this is something that we do need to be aware of when we are using ultrasound in a clinical sense. When physicists come in and bioengineering comes in to test out and do quality assurance on our machines, this is what they're testing for, to make sure that our sound wave, our sound source is all within the normal limits. So intensity is going to be talking about the overall power of that sound beam in a particular area of that sound beam. Okay, so all intensities are going to be reported in units of watts over centimeters per centimeters squared, and we can report it in different ways. We can test intensity in different ways, and we do so by spatial, peak, average, temporal, and pulsed. Spatial, when you hear that word, you're thinking space, right? And that's what it's trying to tell you. Even spatial pulse length. How much of a distance is this pulse occupying? That's going to be the same thing for intensity. So what is the distance or this space? The beam does not have the same intensity at different locations while it's traveling. Do we think that a beam is going to have the same amount of intensity deeper into the body than when it first came out of the transducer? Probably not, right? That intensity is going to be greater at different locations, depending on what we're looking at, depending on how we want that sound beam to behave. With peak, that is going to be our maximum intensity value. With average, of course, that's going to be our average or our middle intensity value. Temporal is always talking about time. So spatial is always space or distance or length. Temporal is always going to be time. So this is taking into consideration the intensity of all time of that sound beam or that sound wave or that pulse that we sent in. So we are including with our temporal intensity, our pulse duration, our listening time, right? And again, our beam is not going to have the same intensity throughout the entire duration, okay? Then we also have our pulse intensity. So this is only taking into consideration our talking time or our transmit time only. For the same reason, our beam does not have the same intensity at the entire duration of this pulse or of this sound beam. So that's going to be the average intensity talking about the pulse duration only. So these are the ways that we are going to report and measure intensities, and they tell us different things. So this will again make more sense to you guys when we are looking at how sound beams behave in a few chapters, but just bear with me until we get to that point. So we said we can measure and report on intensity depending on what we're looking for and depending on what information we're given. So the intensity or the strength of our sound beam is going to vary, right? So how far are we expecting that sound beam to travel? How long are we expecting that sound beam to travel? Those are all going to play a big factor in how we report our intensity, right? How we measure that intensity and what information that's going to tell us. So as I previously said, this is going to be really important in terms of making sure that our system is working within those given operational standards, making sure that we are not implementing any bioeffects on human tissue. Again, this is really important, particularly for OB scanning. We never want to be sending in an overwhelmingly strong sound beam when we're imaging a fetus, right? Those tissues are so fragile and they're so sensitive, and we don't want to have any biological impact on human tissue if we don't need to. So this is something that is done behind the scenes in terms of working clinically, but this is something that you need to be aware of as an operator of these systems, and why it's so important to continuously be getting preventative maintenance done on our machines. So let's talk about some of these intensities that we just were mentioning, right? We said spatial is always going to be telling us information about a particular amount of space, right? Distance, length. We're talking about space. How much is it occupying? So with our sound beam, this is going to be very, very variable. That was a tongue twister. So it's challenging for us to measure and report this. This is something that is going to be affected by our patient, right? So our medium is going to have an effect on the intensity in terms of the space that we're looking at. Think of our sound beam, or think of our transducer as our flashlight. You guys know I love this reference. The strongest amount of light is going to be coming from the center of that flashlight. And then we have this duller, kind of dimmer light that radiates out of the sides, right? So the highest intensity, the highest spatial intensity is going to be coming from that central source. And then the lower spatial intensity is going to be that dimmer light that is coming around the edges of our flashlight. Now, when we're looking at our spatial considerations, we can measure and report our spatial peak intensity. This is documented as ISP. This is when the beam's intensity at the location of its highest is what we are looking for. Anytime we're talking about peak, that means we want to find out what is that maximum value, what is the limit of that power in terms of space, and where did that peak occur, right? This is always going to be higher than the average, because the average, if we're thinking of our flashlight, is taking into consideration those lower intensities from the edge of that flashlight, those dimmer radiating lights from the edge. So that is going to be our average intensity. That is ISA, and that is taking the average intensity across the entire cross section of the beam. So if we look at our little picture here, this is our flashlight, right? This is our transducer. So we know our beam is going to be really intense centrally, right? So as it's traveling, going a distance, whoop, we kind of meet our maximum, right? So that's going to be our spatial peak intensity. But when we're looking at the average, right? So what is that average value of that sound beam? We're taking into consideration that cross section of the flashlight. So we're taking that highest intensity, the brightest central portion of our flashlight, but we are also taking in the dimmer kind of rim light around all of it. Next, we have our temporal conditions. So again, temporal is always talking about time. So this is looking at the time of the entire sound beam. And again, this is going to be very variable. Intensity is very challenging for us to measure regardless, especially when we are looking at measuring that through human tissue, it doesn't really equate as a standard value. So when preventative maintenance comes in or bioengineering comes in, they do all of these tests on a standard phantom, and that's as close to human biologic tissue as we really can get, but it's never going to be 100% precise because we can't mimic that intensity that we would get with real human tissue. So this is why spatial and temporal intensities are never fully going to be 100% accurate. So temporal considerations, very variable, hard for us to measure and report. When we are looking at time, we, again, similar to the spatial considerations, we're looking for the peak intensity and at what time that occurred. So we're no longer looking at what distance that occurred at, we're looking at what time that occurred at. We are looking for the average intensity, so similar to the average spatial intensity. We are looking at the cross-section of time, the overall time average of that beam. We are also looking at the pulse average intensity, and this is going to be the average intensity during pulse duration. So we're not looking at our listening time with this. This is just our pulse duration, just our transmit time. And then also our temporal average intensity. So with this, we are looking at the average of time in general. So this is our transmit and our receive time, or our talking and our listening time. And then we also have combining the two, right? Because when we are sending in that sound beam, we are looking at it, its power and its strength and the intensity of it over a period of time and over a period of distance. So we want to be able to combine those factors and those considerations to get more descriptive information on that intensity, right? On how strong that sound beam is. The more factors we can report to get a better or a more accurate intensity is going to be better. So we do this obviously for our bio effects. This helps us to provide a little bit more accuracy in terms of our measuring and our reporting. So we're going to combine these considerations, right? So I is always standing for intensity, and then we have our little abbreviations. So we have SPTP, we have SPPA, SPTA, SATA. That is telling you what information we have gathered in order to calculate that measurement. So ISPTP is spatial peak, temporal peak. This is going to be the greatest intensity value that we're going to get because we're taking the two peaks, right? So we're taking the two maximum values. This is going to be measured at the location where the intensity is its maximum, and also at the instant in time when that most powerful part of the pulse passed by. Lots of P's with that sentence. Our ISPPA, this is our spatial peak pulse average. This is when we are taking the location where the intensity is still maximum, so we still have our spatial peak, but we're now factoring it with the average amount of time over that pulse duration, the average transmit time from that pulse duration. Now our ISPTA, same thing, spatial peak. So we're still taking that location where the intensity is its maximum, but now we're doing our temporal average. So that's our talking and our listening time is being factored into that, our average all over time. And our intensity, spatial average, temporal average, this is going to be taking our intensity over the entire cross section of that beam and over the talking and listening time, the average all over time, PRP. So that is going to be obviously significantly lower than our SPTP would be, right? Averages are always going to be lower than our maximum values. And then if you need a little bit further clarification on the intensities, you can review in your textbook on page 74, the 10 commandments of intensity. I'm not going to be testing you on that information yet, but that will come up in the future. Also free game for your final exam, this 10 commandments of intensity. It may help your understanding of intensities, but if you find that it confuses you more, just let it be. Don't stress about it too much, but it may help you. If you feel like it's overwhelming you, then just ignore it for right now and stick with the previous information in the chapter and also the lecture PowerPoint slides. So this stuff is very confusing. There is a lot of new characteristics that we're adding in here. So you're probably just getting the understanding of what regular period is and what regular frequency is and how that behaves with regular wavelength. And now we're kind of taking a right turn and we're going, 10 steps further with our PRP, our PRF, our pulse duration, duty factor. So really, if you feel like this PowerPoint was confusing for you, go back, make sure you have a strong understanding of the 7 sound wave parameters, and then understand how that affects these 5 new pulsed wave parameters. Any questions about this stuff, I am more than happy to answer it for you guys. I like to use like my little references, like the flashlight in the hallway. I use the highway a lot too. So if you feel like you need a little bit more of a reality reference, more than happy to help you with that. Also, a bunch of you guys have reached out to me about PowerPoints in the other class. You have to set your range of date further back. Blackboard only considers a recent recording within like 3 or 4 weeks. So just set your date range further back and all of the recorded lectures should pop back up for you guys. Any questions about this stuff, please feel free to email me and I will see you guys on Wednesday.